Jim, thank you very much. Jim is going to enlighten us more than you ever expected about ES, Sporadic E. Over to you, Jim. Thank you.
Thank you very much. Well, firstly, I'd like to thank you all for getting me up into Scotland. I can understand about 10% of what people are saying to me. It's a recalibration process, but I'm sure we'll get on. So tea break over, back on your heads, everybody, because there's a lot to take in here. So what I want to do is to say, obviously it's being recorded, so this is one of those talks where I want you to use it as a way of saying, there's interesting stuff going on here. If I want time to sit and think it through and work it out, look at the thing again, or email me or ask questions as we go along, because it's not something you'll get into immediately. That's just my excuse for saying this is a talk which has got a lot of detail in it, but it's worth listening to, because at the end of this, what I want to do is to say, when the new season opens up, and you're thinking about Sporadic E, it's worth thinking about some of these things that are really going on up there as to how to judge your operating habits and how to make use of the opening when it takes place. In other words, Sporadic E isn't just as simple as, oh, there's an opening, let's work somebody, and so on. There are ways of, I won't say predicting it, we're not quite there yet with the prediction because there's a lot that we still don't understand, but there are ways of explaining why some of it happens where it happens. So the thing for me about Sporadic E, as some of you probably know, I worked in the seaweed business professionally, and what the game was people would come to me and say, look, Sporadic E, there's a whole range of red sky at night proverbs about Sporadic E. People say, oh, it's to do with thunderstorms, or it's to do with this, that, and the other. And it is to do with, unfortunately, a lot of things. There's a lot of stuff that goes on that could have an impact on Sporadic E. So I thought, being a bear of limited ability, I will concentrate on the bits that sort of happen here, which is the weather bits, and there's another bit up there which is sort of vaguely related. So the point is, I'm going to focus on those items, and there are many other bits which are well researched by people who are professional ionospheric physicists. So I'm not going to tread on their toes, or should we say steal their thunder, but this is the bit that I can steal some thunder down here. I can even make it. So what we're going to do is to look at some of these things. And the reason why those things are important is that if Sporadic E was simple, there would be Sporadic E in the summer, in the morning and in the evening, like we're used to, and it would pop up everywhere. But it doesn't. It is sporadic, and it's called sporadic because it's sporadic in location as well as in time. So I've had 30 years wrestling with this, and I still can't do it. But I can show you some things which suggest where we're heading next. And some of the things where we're heading next are actually really quite interesting. So we're going to look at the fundamentals of Sporadic E, which is it's believed that turbulence generated by weather features can propagate up through the middle layers of the atmosphere, these atmospheric gravity waves. So it's like a turbulence that propagates as a vibration, if you like, as a disturbance, and can be detected up here in the ionosphere, but where the ES lives. And the significance of this is that when you get up here, this turbulence interacts with, it's, if you like, modulating something called a semi-diurnal tide. So in the atmosphere, because the way the Earth rotates, the side facing the sun obviously goes round with it, but that bit of the atmosphere is heated, so it expands and it imposes a different wind regime at the height of the E region. Now, this wind regime would in itself give you your twice a day Sporadic E events, your timetable, if you like. It's not a rigid filter type thing like a 7300 or fancy digital filters, but it is a higher probability period of the day, and that's to do with these semi-diurnal tidal winds. But if that were the case, as I said, you'd have Sporadic E everywhere. There wouldn't be any reason for it to be necessarily specifically located in one place or another. So there's something else that plays a role, and that is this. that gives it a locational input. Now, the interesting thing here is, as you know, we now have found out how to forecast the weather. I wasn't sure whether I'd get away with that, but I'm going to stick with it. So yes, Monsieur Le Poisson has got a lot to live up to. So the point is that since we can forecast the weather using the modern mathematical models and so on, there's a lot of detailed information about the state of the atmosphere going forwards that's actually fairly reliable. So perhaps could we not use some of that information to look for where these gravity waves might be generated and where we might expect sporadic E? So the whole point of this exercise is to say, can we examine this a bit more closely to see what is going on up there? Well, this business called wind shear is a phrase that describes a change of wind speed or direction. And this talk isn't about the physics of the sporadic E wind shear process, but it's fundamentally, if you look at an ideal case where you've got wind blowing in one direction at one height and in the opposite direction at the other height, then because we're blowing things like this, the ionization from meteors burning up, which are charged particles, those winds are blowing charged particles through the Earth's magnetic field, and the state of that is represented by the K index. So we've got a situation where wind blowing a charged particle in that direction will impart a motion on it because of the magnetic field, say downwards or down the field line, and wind blowing in the opposite direction will impart a motion coming upwards. So you tend to converge the ionization, and eventually you get a patch that's dense enough to give you a sporadic E patch, an activity on the bands. But that still doesn't say why it's where it is. And the why it's where it is bit seems to point to this effect setting the timetable and this effect setting the location and giving you enough of a convergence to give you some sense of saying you're more likely to find sporadic E there and not there and so on. But we don't know exactly which bits of these weather features are important, and that's what this whole exercise is about. So to start with, a quick look at some ionosons. There's a lot of stuff available that you've no doubt gone online and looked at. Ionosons from Chiltern and Fairford and places like that. There's a brilliant network that the professional researchers make available to we amateurs. And I've tried to find ways of doing a bit more with that. The second thing, I developed this idea of taking the complexity of that and distilling it into one indicator that I've called the E's probability index, which is kind of a locational thing. And that's what this map is down here. And then the third item is the embarrassing bit, which is where I've tried to verify that. Now, verifying an idea like a probability index can go one of two ways. It can say, oh yeah, this is good, we've shown that it's a value, or if you choose to do it during February and March, when I'd finished writing the programs for it, which as you well know is a high point in the sporadic E calendar in the Northern Hemisphere. So we're kind of grappling about in the noise, really, but I think it shows some promise, so I'll tell you why that's going to happen. So let's just have a look at these tidal winds. Now, this schematic is really the thing to go away with. That the debris from meteors, as they burn up and produce the ionization, can be converged into these denser patches. But usually it's only because of the filtering effect you get with weather-produced gravity waves coming up and interacting with this tidal node. Now the tidal node, this semidonal tidal node, slowly descends with time. So that's the thing to remember. So operating tip number one is if you're working sporadic E and you suddenly hear the band open, there's only one way that distance can go, your path distance, because the layer is descending in height all the time. So your longest paths are going to be quite likely at the beginning of an opening. So that's something to go away with. As it comes lower, then you've had more time, if you like, sweeping up. Think of the meteor debris, the ionization as the fuel. And as this tidal window, modulated by the weather bits, descends, it has more time to compress this into a thin layer. So as you get lower, the layer gets denser and more likely to produce E's. So that bit feels fairly logical. Any questions so far before I get too far away from this? Because this is the key point for all the rest of the diagrams. So the idea is that we should perhaps look at some of these things and see what it is that makes this of value to us as sporadic E operators. Here we go. So the initial formation could be as high as 140, 150 kilometers. And then it slowly levels off as it descends. But it can increase quite rapidly once you get down here. But equally here, it's very sort of flighty. It's there 1 minute and it can dissipate quite quickly too. Sorry? Oh, sorry, Terry. Yes, forgive me. I haven't been saying this. So the top of the graph is labelled 150 kilometres altitude, and the lower bit is about 90 kilometres, where it tends to level off in altitude. So between 150 and 90 is the sort of window. Now, what we find later on is that at about 110 is where we end up with the maximum value for the FOEs. This frequency along the bottom of the graph is FOEs in megahertz. So this is the critical frequency of the E's layer. Now, bearing in mind, we're not, as amateurs, sending a signal straight up and down again. We're going in at an angle. So you get better performance than that value, because you'd think you wouldn't get any sporadic above 12 megs or whatever, because the scale goes from 2 megs up to 12 megs. In fact, there's a ratio which has been borne out empirically by looking at the DX maps plots of paths, which suggest for FT8 and things like that, you could probably use on digital modes 8 times the frequency to find out which band. And on CW and sideband, it would be 10 times. So that's a good figure for CW and sideband to have in the back of your mind. Now, the thing about this is, if we're going to look at this in relation to the semi-diurnal tidal winds, these are 2 periods in the day, one in the morning and one in the evening, when this descending tidal wind caused by the Earth's rotation and the bit of the atmosphere facing the sun being heated more, that tidal node descends with time and gives you typically a reason for the morning E's window and the evening, late afternoon, early evening E's window. And that's driven by the semi-diurnal tide. So what makes that? Well, this heating thing isn't constant, because in the winter you've got lower solar angles, so you've got less heating. So you'd expect the strength of the semi-diurnal tide not to be the same in summer and winter. So could that be a reason why we're getting the performance that we do in the sporadic E calendar? It's not actually the only reason, but it certainly means that one day can be different to another depending on the larger scale heating. But if you looked at this, you would think everywhere would get 2 openings on E's every day, and we don't. So you do get the opportunity for weather-generated turbulence to modulate these zones. And that can give you a steeper period of descent, a more active focusing of the ionization, and give you a better reason for more sporadic E. And the same thing applies in the evening. So you've got 2 periods when, for various reasons, due to this wind shear effect. So when you see wind shear and the mention of jet streams, it's not the wind shear on the side of a jet stream that aircraft fly through and things like that. It's the wind shear up here in the E region at about 100 to 150 kilometers that we're talking about. So you can simplify it by saying you've got these 3 things going on, descending places where the wind shear can happen. There is, underneath all that, a diurnal. In fact, there's several other tides involved up there, and these are the main ones, but there are others. So can we perhaps look a lot more closely at weather systems to see if that can give us some insight into where sporadic E happens? The other thing I'll add is that you might say, why doesn't it go any lower? Why doesn't it keep coming down? And one of the reasons is that as the layer descends, the atmosphere is denser, so there are more molecules around, and the ionization recombines more quickly. So in effect, the sporadic E layer is eroded from below at about this 90-kilometre height region. So you tend not to see much below that. So when you look at your ionoson plots, we've always been used to looking at these things as single times and looking at the familiar hooked echoes that you get when you plot the data from an ionoson and you find out two essential figures. The FOEs, which is this critical frequency for the E's patch. On this example on the slide, which you probably can't read from the back, it's 4.6 megahertz. And the height, or the virtual height of the E's layer, which in this case is 105 kilometers. So in other words, the information we need at any time from any ionoson is there for us to see what height we think the E's might be at. So perhaps we can look at that data and make something of it, bearing in mind that some of us, and many of us will, up till now, have been aware of taking, say, a nominal height for E's, 110 kilometers, 120, whatever the figure is. We've all got that figure in the back of our mind. But if you change the height of it from 140 kilometers, that would calculate at just over 3,000 kilometer skip, and 100 kilometers, you get just over 2,500 kilometers skip. So the height of the E's layer is really important. So anyway, let's see what we can do with that. This is what happens if you plot on this graph. The black line is the height of the E's layer. Again, the axis on the left is from 80 up to 150 kilometers at the top for the y-axis. And this is 24 hours for a whole day. And you can see at various points you're getting slopes in the height of the E's. Okay, there's noise. It's like a noisy signal with ups and downs on it. But if you draw a mean line through it, you can see there are several points where there are sloping lines going downwards. And this is a measure of this sloping tidal wind shear zone. And then the background colours here represent that broadly sort of 10 times figure for CW or sideband. So you can see as you come down a slope, you'll get a peak. You might not retain it. You might get other minor ones that don't quite reach enough value. You might get other ones in here which do. So the colour here, green, these zones are 6 meters, and the 10 meter zones are this pale bluey colour. So just by doing that, you can see a lot more about how a sporadic E patch works, you know, how it, but this is one place. So how does that affect us, you know, in terms of calculating what a path is going to be like? It's really difficult. So I thought the only thing I can do initially would be to look at these things for one station and just take the middle of the month. And so I've taken the 15th of the month, and in January, these descending nodes are present, but it's very limited in time. For June, a lot more of that time produces values high enough, but yet the descending nodes aren't very significant. So that's another question to answer. But it's still nonetheless there. March and November, the midway seasons, it's a bit noisier, and you tend not to get so much going on. Now, why is that? That's another question to answer. And February and September are very noisy with no very strong indications of descending nodes. There's probably a bit of one there, but you can see how noisy this data can be. So it's not the only answer, but it is a way of saying why you might get sporadic E one day and not another. Because if you can look at these differences, and that's only over one ionoson, you know, you can imagine what it's like from place to place. So I decided to plot something else, which was to produce these color-coded plots through the range of frequencies from 2 megs up to 9 megs, which is on the right here, and from a height of 80 up to 150 kilometers on the y-axis. And if you look at the color of the dots, you can pick out these green dots here, which equate to 5 or 6 AM. You can see starting a descending pattern here, and then it sort of fizzles out. In the blue, in the early hours of the morning, between 1 and 3, there's a lot of low-level stuff going on at a very low height, at about 90 kilometers. Whereas up here, the highest one is 140. So we've got evidence of a descending period here, and this underlying bit here down at 90 much, much lower, which is probably that diurnal legacy of the previous day, which hasn't quite eroded away yet. And then we go into this phase here. There's a slightly orangey coloured circle or two there, which is what happens to the green stuff. Because as you go along this axis, you go from greens, which are 600 or 700 in the morning, to 9, 10, 11, which gets you into the oranges. And then the last orangey bit looks like it comes up to about here somewhere, which gets you towards about midday. So there's your morning phase. And then you get a new one starting in the late afternoon in purple at 1600 and descends, and that peaks up much further. And that ends up at over 8 megahertz. Well, 10 8s are 80, so that gets you into 6 meter territory, you know, quite comfortably. And that was a pretty good opening on that particular day. So here's an example of two descending tides, which if you just take the data for one ionosonde, you can see it happening right there in front of your eyes. You've got a Sporadic E 2 layers descending. Now, the ones that I've looked at over the few months I've been getting the program to work, the tendency is that you get a very finely focused maximum value in a very thin layer. You don't get it spread all the way through the height range. So making Sporadic E will tend to favour a fixed value. So this is where you can use your if you had to pick a single value, take somewhere between 105 and 110 kilometres as your height for Sporadic E. Right, have you all gone off yet? Do you want any more? Because I've got a couple more. I don't know if I can get away with this. Right, okay. So if we do this coloured version for January, look at this fine business job going on here in January, all the way up to 7.5 megahertz, again focused on about 110 kilometres height. But that's something that sprung out of this thing in purple, all the way back here at 130 kilometres, started showing symptoms at 2 megahertz, and then descended to end up with a Sporadic E patch at about 16 to 1800 that got us, you know, as high as 7.5 megahertz. So there's your midwinter. This is 15th of January. Now, I'm not I have got to confess, I don't really know why this midwinter anomaly happens. If you expect the summer June one, which is another very strong one, but again the colours suggest that's a morning one and not an evening one. I haven't yet got anything to tell you about why morning or evening should be better. They are quite often different. You don't necessarily get the same strength of opening in those two sessions. So whether scooping up all the ionisation in the morning depletes the stock and you've got none left for the second descending phase to produce, I don't know. So that's something to look at over the years. March and November don't look too exciting, really. There's a little bit going on. So in other words, when you look at stuff, you can see Sporadic E does happen even outside the season, but it maybe doesn't get to high enough values to be really exciting for VHF. February, this one here, the top of these two, shows it all tries to get its act together and then goes a bit random around the middle of the day. And September, we've got just a random sort of spread of values between 2 and 4 megahertz at a height of from 90 kilometres all the way up to about 140, and it's just disorganised. There's no sign of a layer, it's just scattered around the shop. So there again is a message about, okay, I've taken 15th of the month just because it takes time to process all this stuff. But if you think about what that's telling us is there are some days when you have no apparent organisational structure in the wind shear at all. So is that because of lack of weather triggers? It shouldn't just be that, because there's always going to be a semi-diurnal tide of some value up there. So is it that some days the semi-diurnal tide just breaks down and doesn't function properly? It's really an interesting problem to take away for the next sessions. Right, okay, so any questions on that little bit about a new way of plotting ionosondes before I move on? The data, where do I get the data from? This is data taken from the ionosonde network, and what I do, I've been in touch with the people who run the Lowell ionosonde database in the States, and all the ionosondes measure and send their data to that big collecting centre. So in order to avoid amateurs going in and just every 5 minutes checking it, what I've done, I've written PropQuest, so that, or my colleague has, so that we go in every 10 minutes just once and pick out the data for a selection of stations for Europe and a couple in the States and one in the Caribbean, and keep the archive going that way, and then I plot the data. They're a hugely impressive bunch of people. They very rarely fail. The PropQuest website has been going for donkey's yonks now, and we only occasionally have complete fails when their server goes down or something like that. But that's how it's done. If you need details, send me an email and I can tell you. Right, so the next challenge was to see if we can get this all into one figure, and that's something I call the ease probability index, to try and highlight areas where ease might happen. So that was plotting on a map. There's a coloured map here on the left, which has got different shadings according to the value of this EPI index. So where the index is high, with a strong jet stream, say, it colours through yellow, purple, into silver, and the highest values here over Spain, and so on. And you'll notice they follow a pattern, which if I told you what the weather map looked like, that would be the pattern of an upper air jet stream. And when I worked a station, you can plot it on the map and you can see if your path in the midpoint here has one of these high values associated with it. That's the ideal picture. Doesn't always, but that's... So the EPI index is a function of weather and then a factor, which is arguably and unkindly called a fudge factor, but it contains things that aren't to do with weather. So the weather bit gives you the locational bit, and the F factor tells you things about the state of the K index and stuff like that. So it may be modified by things. The whole index is capped to a value at 100 units, and everything happens between. And the modifying fudge factor, if you like, the effects of other things, is to do a set at 1 if I don't know what to do with it yet, but it ranges between 0.5 and 1.5. So it can adjust the final figure just to give it a bit of weighting. So in other words, if you came up with a real slap-bang racing certainty for Sporadic E and had a value of 100, and you were in the month of February, you'd want to claw that back down a bit to lower the chances. So that's what those things are used for. So the weather things, let's just list a few of them. So the weather bits are affected by jet streams, vorticity. Now vorticity for some of you might be a strange word to put into something to do with amateur radio, but it's the amount of wind shear on the edge of a jet stream, because that can create turbulence. So you imagine if you were standing on the side of a little stream and there was a strong current flowing through the middle of the stream, and you put a stick across the stream halfway from the bank to the middle, the bit in the middle would go quickly and the bit near the bank would go more slowly. So the stick would turn with the flow, and that is imparting spin onto the stick. So vorticity is being added to things, and that is what vorticity is in a weather forecasting sense. Change of the pressure pattern is to do with a falling chart, a falling barometer or a rising barometer, if you're changing the mass of the air there, if you're altering the pattern. And the speed of change of the pattern or the absolute value change has an effect as well. Then we've got the convection parameter, which is all about showers, because the original idea, when somebody came and sort of tapped me on the shoulder about this, they said, well, it's all to do with thunderstorms. You find a thunderstorm and you'll find Sporadic E. And that may be true in a few cases, but to be honest, since I started looking at this, and I started this in the late 80s, in all that time since the late 80s, I've only found one occasion where a thunderstorm has been remotely close to a Sporadic E patch, and that was over Turkey in the summer when you had an intense pulse-type thunderstorm, and you imagine the thunderstorm contains hugely strong upcurrents. So there was somebody involved in aviation. I'm not sure whether your helicopter's got to the top of a thunderstorm ever, hopefully not, but the vertical wind speed in a thunderstorm could be well over 100 knots. You know, you can get tremendously strong updrafts, and when that reaches the stable top of the atmosphere, it's like banging a drum, and it sends ripples up, and it was believed that those were really crucial in sporadic E. And what I think has actually happened is that they're crucial in the summer season, and you tend to get these days of sporadic E in the summer, and you hear about thunderstorms around the shop, and you go, oh, that's going to be thunderstorms. But when you look at it on the map, there have been some stupendously good openings of sporadic E when there hasn't even been a cloud in the sky, let alone a thunderstorm. So of all the occasions, if I had to pick one thing, I would pick jet streams as being the guilty party or near to the guilty place. And just don't know which bit of it yet. So anyway, convection parameter is in there just because historically that was the red sky at night part of sporadic E. But evidence suggests, well, you can go with it if you want, but I don't think it'll help you too much. Stratospheric wind regime. Remember that opening schematic where I had the little ellipse saying AGW, the gravity waves that propagate up through. The stratosphere has a different pattern in the winter to the summer. And you get this sudden flip around the middle of May, and then it flips back again in the late part of August, early September, about the first or second week in September. So you could think, oh, that'll be it then. That's what turns sporadic E off and on. And then you find something else and you think, oh, well, what about in the middle of the winter when you get these random openings? Well, you do get things called sudden stratospheric warmings where it does a sudden flip again, but for a very brief period. So you think, oh, that might be useful. But to be honest, it could be entirely coincidental. But since these gravity waves have to propagate through it, the physics suggests we should at least try and look at it. But it's difficult to separate these things out. But it's something that's in the deal. So stratospheric wind regime may sort of reveal itself. And then the upper ridge index is more about when you go off in an aeroplane and they switch on the light saying, fasten your seatbelts, we're expecting some turbulence. You get a lot of turbulence on the axis of an upper ridge pattern in the atmosphere. It can be a turbulent place. So I thought, well, I better put that in there anyway. And a lot of sporadic E tends to occur near upper ridges. But the more I look at it, the more I think you're on the edge of the jet stream ahead of the upper ridge or the one coming in behind it, rather than the ridge axis itself. I don't know enough yet, because one of the problems we have is that we're looking at weather charts that come up with values of these parameters all over the globe, or as an ex sort of boss of the Met Service, who was a Norfolk bloke, and he said, one day we're going to have satellites that cover the whole globe. And I thought, I know where you come from. He's a Norfolk boy. So covering the whole globe gives you a chance to make the mathematical models of the atmosphere work on this global scale. But when it comes to sporadic E measurements, we only have a few ionosons scattered about here and there. So the chances of expecting a good sporadic E opening to sit right on top of one of these ionoson stations is a big ask. It will happen one day, but I've never seen one right over the top of an ionoson station that's got up to, say, 2 meters, for example. We've gotten fairly well up the scale, but not enough to get to 2. So I'm not going to spend long on this, but if you plot this left-hand chart here, has got black lines on it, which are the equivalent of isobars up at 300 hectopascals, or where the jets fly. It's a jet stream height. And the green shading is the jet stream. So you can see sometimes there's jet streams all over the shop. You know, you've got so many places where you could expect a jet stream to help you out with sporadic E. And bearing in mind what I said, on the edge of a jet stream, you've got a lot of shear vorticity. You've got a lot of turbulence going on. So I thought, oh, I know what I'll do. I'll plot vorticity as a separate parameter. And you can see vorticity tends to happen in very thin ribbons. You imagine having a cup of black coffee and stirring in a few drops of milk, cream, and seeing those swirls just stirring about. It is incredibly difficult to get the models to represent this really accurately, and then to expect one of these to be in exactly the right place for sporadic E. And then you have thunderstorms, which are these magenta shaded bits on this map. They tend to happen ahead of upper troughs. Thunderstorms, if I had to sort of knock thunderstorms on the head, it would be to say this. thunderstorms have a limited life cycle of 1 to 2 hours, say, for an individual storm. They'll produce the upcurrent, they'll produce the turbulence, but they're very rarely stationary. That one I found in Turkey was a stationary supercell thunderstorm. Most thunderstorms, like the one we had, the few that we had recently, are in an air mass storms, which move with the wind. So they're not going to be in a place long enough to get this stuff to converge and focus the ionization to make sporadic E, because they're moving. So they're not in a place for long. That's why I think thunderstorms haven't really featured too much. And then we have the fiddle factor bits, which are time of day. Well, we're fairly good about that. We know this is a semi-diurnal tidal thing. What we don't know is why some days are better than others. What makes that change? The seasonal factor is a little bit of both. Topography, well, that's fixed. We're not making mountains necessarily, so we know where they are. The dip angle of the magnetic field, we know a bit about what that's, well, it's changing, so I'll have to update the figures, but I was kindly provided with a set of data for that. The KP index is changing all the time. Meteor input is changing all the time, and I think the solar flux index. So there's lots of things we can still tinker with. The interesting thing is that there is a growing feeling that instead of booking the first week in June off for sporadic E, like everybody used to do, because all these meteor showers, little minor meteor showers, all converged at that time, it may have been coincidental in some senses, and it's probably going to have been better to look at the background meteor content, the stuff that's coming in all the time, because when you look at that, you'll see that does follow a path, if you plot it through the year, which would explain some of the reasons why the season is shaped the way it is. And the RSGB is about to launch a meteor measurement beacon scheme, which is going to be really valuable for gaining meteor input data, which is really terrific. And Mike here at the front, GM3 PPE is involved in that, so you can ask Mike all about that. And that's a great asset to have sort of coming to the table. But if you look at an article I did for Radcom Plus last May, I listed this background meteor and showed a graph of it. And if you take an arbitrary value of that input, it's like the fuel for sporadic E, so why shouldn't it come into it somewhere? You'll see that you do get a little blip in the middle of winter, and you get your main season when you get your main season based on this. But it's never going to be as simple as that, because that tells you when the coal man has delivered the coal into the bunker. It doesn't tell you whether you've got the gravity waves coming up to make the E's with it. You know, it could just stay there and slowly recombine. Anyway, so this is one I prepared earlier. Well, this is last May, a CWQSO I had with an IS0, I think it was. And when I plotted that on the index, the halfway point had a little hot spot on it, but it may have been coincidental. But you can see there's a lot of stuff going on here. There's these hot spots all over the place, mostly to do with small-scale jet stream and vorticity generating areas. So the atmosphere is a really turbulent place. So looking at this is a different way of plotting things. Just very quickly, you can see more clearly on this one where the axis along the bottom is the FOEs, goes all the way from 2 megs to 12 megs, and at the bottom here it's 80 kilometers, and up the top of the y-axis 150. And you can see very clearly we get some stuff starting. It produces enough to get to 10 meters, which is this bluey color. Then it goes to 6 meters, and then it goes to 4 meters, and it ends up at a value of about 12 megahertz at 110 kilometers. And this is for CW and SSB, so it doesn't quite get into. You'll notice the change over to 10 meters happens a bit higher in frequency, but that's all the differences between those. But it's a really great way of examining ionosons to see what a sporadic E patch looks like, if it's going to be there. So when you combine it with these other wonderful things, you can see you can get, on that day, for example, that path that I worked down into the central Mediterranean at Roquette, which is northeast Spain. You can see a really strong intensification as you come down this morning semi-diurnal tide, and it goes through the colours of 10 meters, 6 meters, and then 4 meters, and so on. So I'm hoping to run this more frequently, and one day perhaps for some selected sites I might put it on the PropQuest website just to display it, because there's a lot of data in here and it takes a while to run it, and we'll have to make sure we don't overload the work server. Not sure whether they know I'm running it on the work server yet. So shh, this isn't being recorded, is it? No, we're okay. Anyway, so this is what it looks like in the time domain, and you can see that this I've shown because it was an evening type of opening here, which starts at purpley areas at 135 kilometres and very quickly comes through to the end here. And then it's overwritten the morning one, which is this orangey colour down the bottom here, which is probably the continuation of the diurnal tide at this lower height. So it's quite complex what's going on there. But the important thing is, if you look at these things plotted as a time source, you'll notice there's only one way sporadic E heights tend to go. If you draw the trend, you'll see they go lower in height as the event develops. So that means if you're first on the, this is so important, if you're first on the band, you'll get the better paths, you'll get the longer DX. But I have to say, if you're on a multi-hop path, you've got to think really carefully about what the other hops look like. This is only going to be one hop that you look at, and when you make up multi-hops, they're not necessarily going to be in the same state, but they will, as the Earth turns and that tidal window moves, you can guess by how many hours ahead these other points are, what their things might look like. Anyway, so here's one only a couple of days ago, and this was lifted off the DX cluster, and here's a guy in the States working down into the Caribbean, and his halfway point is on the edge of this little miniature jet stream circuit here, and edges of jet streams seem to be coming out as places to look for. Now, why it should have happened there and not the edge there and so on, still a lot to be done, but it shows the importance to me that vorticity might be a place to look at. You've got all these other areas going on, but why did that path happen? So we've changed the way the website works. You put in your call sign and the locator square, and you put in the second station. You choose a doesn't work on single hops, but you choose a multi-hop distance, and you compute that, and it produces this, a little list of the two stations, the locators. It gives you the frequency because you've ticked that radio button, and it tells you the distance, and it tells you the time up here in the top left of the map and the KP index. And it allows you to press that and form a PNG screen grab. So if you work something interesting on 6 and want to put the path in, then put the path in, click that button to get a screen grab, and you'll get a screen grab, and you can add that to your file of QSOs or log it in magazines or whatever to explain the way things happen, and feel free to do that. This help file up here tells you a bit more about things, and then we're changing how it plots multi-hop ones now as well. So these are the reflection points from the ease patches. This was a 10-meter path a couple of days ago. I don't know if it's significant, whether it was sporadic E or whether it was a normal FOF2 sort of thing, but certainly from an ease point of view, you could explore it and say, well, those two correlate pretty well. That might be all right. It's early days. This is an experimental bit. Right. So last bit, this I plotted for the month February to the end of February to see if there was any clustering of E's, which are these top half of the graph. These blue lines show it got to 10 meters, which is this blue area here. There's one on 6 meters, which is a lime greeny color there. So A and B were both good ease days from the measurements. This one was well forecast by the EPI index. This one not so. So I looked at those, and then this occasion here, nothing at all. So why did that day not happen? Well, the first day was on the edge of a jet stream, so I'd obviously forecast that. This one wasn't quite so obviously on the edge of a jet stream, but it produced a good result, the best result of February. So the question is, got to look a bit more at why that happened. The one that didn't do anything is right in the middle of an upper high. So straight away, we've got a really good clue as to which bits we need to look at on the on the maps. And then when you plot that first example, you can see you've got multiple different sloping regions. So that's another area that I'm going to investigate, and whether there's any importance in how rapidly these slope as to what the final convergence factor becomes. And this is, you know, showing a nice bit of focusing late afternoon, and there you have it. And I won't go into those. This is a case where we didn't forecast it quite so well, but it produced a very good descending node, and that was wind coming from a different direction. So I'll have to look into that. Could have been a mountain wave thing with a southerly wind blowing over the Pyrenees. And the one that didn't produce anything in the middle of the high, there's no response from Sporadic E at all from the ionosonde. You know, it's just only 2 or 3 readings. So middles of big highs are not good. Cloud. So, and then truth. So this is the last bit. You've all done very well. So the last bit is, if you plot, and it's only in the middle of this week that I've finished getting the data for March in. So this is February and March. And if you looked at scatter plots and thought, oh, we can do something useful with this, you'd probably think, right, okay, let's pack it all away in a box and think of something else to do for a living. It's happened to me quite a few times in my career, by the way, I should say. So the EPI index on this top left-hand graph, EPI index along the bottom, the height of the E's, the FOEs rather, is up the side. So just to clarify that, 2 megs at the bottom left, up to 20 megs at the top, and going along the axis, an EPI index from 0 to 100. Ideally, you'd want to have something that went up like that. And it's sort of looking as if the real answers are sort of drifting slowly upwards with increasing value. So we're getting some bits right, but it's not very focused. And this is the 2 quietest months of a whole Sporadic E season. So I'm just tinkering with the noise, really. But it's a bit of fun testing the system to see what works. This is the strength of the jet stream. And you can see anything that produces an FOEs on the ionosonde doesn't necessarily require a strong jet stream. So what's going to be interesting, now I've finished writing the software, is to see when we go through a proper season, whether there is a stronger link between the strength of a jet stream and the FOEs that you get. So how good an opening do you get? Is it a sort of a proxy for a measurement of the amount of turbulence? And then this one I looked at the vorticity, and that seems to be scattered about quite a bit. So I'm not sure that's going to do much for us, but it's there. And then this one I thought, the direction. What about the direction of jet stream? Does that have any impact in it? Now that could be just telling us about weather. You know, this period had weather from that direction. You know, it might not be necessarily saying anything too interesting, but I'm going to come back to that in a moment. Then I looked at the contour change, whether the pressure was falling and rising at height and what was going on. Not much going on there. The surface wind doesn't seem to have much of an impact on it. A turbulence index doesn't seem to have much of an index. I'm almost at the point where I'm about to take my own head off at this stage and give up on it. And then the height of the E's seems to be coming up to something with a peak at about 110 kilometres for just 60 odd events, but that's not many events. It'll be interesting to see what that looks like in the summer when we've got a few more things. So then I went back to this business of height. Now on the top of this graph there's a map of northeast Spain where the ionosonde, and on the left, on the axis along the bottom here, we've got the direction of the jet stream winds at 300 millibars. Here we've got the velocity going up the y-axis. And these little dots represent, the colour tells you which band you've produced E's for. So a blue dot didn't quite make 10 metres. A pale blue big circle did get to 10 metres. A lime green dot, like that one on the left at 010 degrees, and a whole cluster of them in here did get to 10 metres, 6 metres rather. And then we've got one red dot in here, just this last month, got to 4 metres. And I thought, what makes this clustering? Is that just a function of the jet stream direction, or is there something else going on? And if you look at the mountains in relation to this ionosonde, when the wind is blowing between 350 and 020 degrees, it's that bit on the right-hand end, and this bit here, it seems to produce quite a number of these full-on circles. You then get a reduced area in here. This quiet bit correlates well with the wind coming from this direction, from the sea, and then you get another quieter bit in here from the valley bit, and then another strong bit in here from this direction, so that bit. So when the mountains are close, you tend to get evidence of sporadic E happening when the wind is blowing across those mountain ranges. But this is only a small sample, and there's a lot of scattering going on, but I'm quite straws when you present a load of scatter plots like the last set. So this one is kind of interesting because it does show that there may be some relationship to nearness of mountain ranges. So I think what will be most interesting is to look at this site and a site without mountains nearby to see what that tells us about the usefulness of the mountain wave factor in causing these gravity waves. So that I took as a small positive. This one I'm not going to say much about, but where you get upper air charts, if you've got a developing cyclonic pattern that's decreasing in value, that's a trough coming in, tends to be turbulent. A big high pressure ridge building tends to be turbulent potentially. So I would expect this to form an axis going from top left to bottom right on that scatter plot. It may not, so that will be interesting to see what happens there. This is saying that 58% of the, or is that 56? 56% didn't quite make 10 meters. 42% did during those 2 months. 2% got to 6 meters, and less than 1% got to 4 meters out of those values. And this is looking at the ease index. If it was less than 50, you got more no ease than ease, but not by much. So we got some refining to do there. When you get an EPI between 50 and 75, there's more ease than not ease, so that's going in the right direction. And when you're above 75, you've got just ease. So I'm fairly pleased that for a noisy data set, that's come up with that. And then the last little bit, big cluster of stuff in March, got to 4 meters. What does that look like? It looks like this. And this bit is a peak in vorticity. This is a turbulence index. This green bars in the middle graph is sporadic E. So they got up to 4 meters here on one day. This is one day, 4 meters. And the probability index followed pretty well the trend of the sporadic E loggings, but it's not exact. Now, what I think happens is it takes time for the propagation of the gravity waves to go up and make the ease after you've given it a bit of a boost with the turbulence maybe. But here's the jet stream, this purple zone at the bottom. So, what next? More stuff, more things to investigate. And I think I'll probably stop there and let you all slide off gracefully, and I'll go back in the hutch. Oh.
I was just going to ask, how do you, when you've got morning and evening peaks, how do you get your multi-hop to the States going east-west? Surely at some point you're going through noon, aren't you? It's not going to help a lot.
Well, that's a really super question. You've got to wait till the steps are paced far enough apart to get, the first hop is going to be in our afternoon, evening peak, and the next one across will be in their morning peak, and there might be enough of the residual stuff from the diurnal tide that doesn't have a peak. So in the middle of the season, you might have enough residual stuff, because you know some days you get sporadic E and it's there through the peaks. It doesn't switch off, it's there continuously. So multi-hop ones, you tend to feel there'll be periods between these peaks when it happens. The other thing is on days when you get weakish activity and only single peaks, I kind of have a vibe that there may be a trend for the semi-diurnal tide to make it a more focused onto a single event in the middle bit of the day. These fleeting ones outside the main season, you tend to, whether it's a late morning peak and you never get an afternoon one because there isn't enough material from the meteors, that could be something. Or it could be just that the semi-diurnal tide. The trouble is, it's difficult enough measuring stuff outside here at the surface in terms of the weather world. You imagine trying to measure stuff all over the shop in the ionosphere. It really is difficult. So this stuff will drop out of having more data to process, I guess, and show which places we look at next. But at least now, the point I've got to is that the programs are written and I just have to put the dates in, press the button, and I've got a new month. And I've got a new single event to examine and things like that. So it's all about building weapons in the armory to make sure I can analyse the things properly when they come in. So I'm hopeful this season is the one that reveals a lot more about what's important.
Probably a silly question. I found that quite fascinating. DX maps, I always switch on DX maps when I go into 6 meters, and you can watch the numbers changing. Where does that information come from, and how is it put onto the map?
Well, that'll be, it's a great site. I use that all the time. And I haven't said, but basically this line here in the thanks to, I'll read it out. Thanks to the many amateurs whose logs tell us more each year. This is the real bit where amateur radio, you might not be doing much building. You might have reached a stage where you can't see the components. You might be doing the hobby differently to how you did before, but it's a self-learning hobby. And putting logs up and being curious about propagation is a way that moves. Because you go back 20 or 30 years, when I first dropped an article off to Pat Hawker down south of London there about Sporadic E, and we really didn't know very much at all then about it. And it's so much has come forward, not necessarily because of what we're doing here, but because of all the amateur logs have built up a picture that we can't ignore anymore. There's so much data there. And the only thing I would say, and this isn't a dig, but when you look at that, and I've just realised, Chris said you didn't speak, Tom, so I'm quite impressed at this. This is good. One of the things you have to bear in mind, if you switch your DX maps on, and you've got digital mode selected as well, it's a bit like a whiteout. You know, you've got so much data that to a propagation studier, it's not so easy to see what the real deal is. So I tend to switch that off in the peak season. I'm really grateful for it in this quiet season, but in the peak season, you just get so much. And a question about how they get the data, they'll log a path from somebody to somewhere else, and they'll use the calculations as to what the midpoint MUF might have been for that path distance. And that will give, if the person logs it as Sporadic E, and this is another thing, when you log your paths on DX maps, you've got to be, these aren't selected as being automatically Sporadic E. You've got to decide what to call it. So if you're not sure, call it unknown. But if you think it might be Sporadic E, if it walks like Sporadic E and talks like Sporadic E and sounds like it, then call it Sporadic E. But look out for signs of TEP going on at the same time as we're currently in now. And when we get to the peaks in the sunspot cycle, it becomes harder to separate out some of these multi-hop Sporadic E paths, say on 10 meters. And the test will be to look at this multi-hop plot system that we've developed now to see if the little circles for the midpoints fit with the Sporadic E EPI index going up. I don't know, some of you I know watch the Ham-Sai thing online. There was an interesting talk there by Larry, N6, I've forgotten his suffix now, but he did a really interesting talk, apologies Larry, which was about a path on 40 meters between the States and Japan using QRP contacts at the other end. I think there was a Japanese QRP contest on. And a huge number of stations came in. This was on one of the digital modes, as I recall. So these were all logged while he was out of the room sort of thing, and he thought, I'll go back and have a look at this. And he's been piecing together some studies which suggest it's related to the smoothness of the ocean surface on the grazing point between the multi-hops. Now, there's been a couple of papers published by some Chinese researchers that have come up with some broad back of the envelope type figures for the difference between a smooth sea and a rough sea. And that's worth following up on, because we tend to, in our mind's eye, draw sporadic E multi-hop paths as a sawtooth, very peaky sort of shape. But in reality, it's very, very shallow. And you've got this grazing angle where it meets the sea surface between the multi-hop paths. And if the sea state does play a part in that, that might be something else to add in. So on this multi-hop display, I'm going to, as well as the circles, which are 100-kilometre radius, to give me a bit of a sporting chance. Because the other thing is, these EPI maps are based on forecast weather maps. Now, we know that forecasts are hugely accurate. Yeah, got away with it for the second time. So they're hugely accurate, but there will be differences in the phasing of a trough or an upper ridge and things like that. So a 100-kilometre radial ring, I think, is a fair go at the moment. But equally, I'm going to put little tick marks across for the grazing incidence points in the middle, because I think that might be quite useful.
Jim, can I just take you up on the multi-hop? Because you do see some interesting things on 6 meters, and I'm just wondering what the mechanism is. And I refer, for example, towards the end of last season, I was working W6 on 6 meters, so, with nothing in between. And this is not grazing off the sea, this is going over the land. So are we seeing some sort of caudal hop, or are the...
Well, yeah. A good question, Don. I mean, I honestly don't know.
Right.
But when we come to the stage now where we can put those two locators on that map and plot and see how it relates to hot spots, the main colours on those patterns are driven by the weather situation. So the positions of jet streams and all that stuff will dictate how it goes. And I know there's a question going to come from, who was going to ask me a question about multi-hop paths? Somebody was going to ask me a question. Oh, he's done it. No, there was another one. There's another one. Well, I'll answer it anyway. The point about multi-hop paths and why sometimes of the year they seem to be better than others. One thing about the paths to the west coast is if you look at where the ground grazing bits are, some of those will be in Hudson Bay, and the quirkiness of that is quite funny sometimes, how that goes. I'm not saying it's the only reason, but bear it in mind when I put the other tick marks on the displays, because that will help to track that down.
So you're saying there may not even be people in some of those places?
Oh yeah, absolutely, absolutely. I mean, this all depends upon people being on. And, you know, that's the one bit that we're not certain of. The fact that there's no record of QSOs from along the route is not saying that there wouldn't be. Anyway, the other thing is the early part of the season, we're coming out of the winter months when you get a lot of jet stream meandering waves going around the northern hemisphere of the planet. And the pattern is such that the wind regime changes a lot from the May start of the season to the middle and second half of the season. And there's a very strong preference for more multi-hop stuff that can go, and it will even explain some of the JA paths. If you look at the EPI index, we've got a problem with the map plotting the EPI values at the moment, if you go too far east, but we're working on that. And once that's in, then we'll be able to fine-tune that. And when I've looked at it in the past and made it up subjectively, they are uncannily aligned for these multi-hop ones. And you think, how can we get lucky? You think a multi-hop, say 3 hops to the States or to the 4 hops to the Far East. You think, how can we be that lucky? And in actual fact, when you look at how many jet streams and curls and whirls in the upper air pattern there are, with its inherent turbulence and all the rest of it, there are that many opportunities. The question is, what makes it work some days and not others? So there's a huge bunch of stuff to come out of it, really. Yeah, yeah. Yeah, we've got one going down the middle.
Sorry, I don't want to keep everybody back from the raffle. I wonder, do you think there's any correlation between the distance we are from the sun during the winter and the summer.
Uh,
And it'd be interesting to know what
yeah,
the E-season's like in the southern hemisphere.
that would, on the first thought, be the right question to ask. On the second thought, it's more to do with the angle of the sun in the sky. So if you think about the amount of energy coming in per square metre, so you take a searchlight, a torch. If I had a torch here and I shone it on the ceiling straight up, the light from the torch would be in a very concentrated circle on the ceiling above my head.
Yeah,
and
I
it would
do
be really
understand
bright.
that.
Now,
But I
if
mean,
you
if you're
tilt it at a lower angle, shallower angle to the roof halfway down the room, that same light is spread over a bigger area. And that's how to look at the sunlight between summer, when it's more overhead.
Yeah, I appreciate that, but I mean, in the southern hemisphere,
They have sporadic...
it's their winter.
Yeah, that's right.
when
But
it's our summer.
Their season is the mirror of ours. So they have their
Yeah, but I mean,
sporadic E-season in our winter.
Does their E-season last the same months as ours? Or is
Yeah.
it different?
Yeah, no, it's the same. It's not the same calendar months, but in terms of their summer, it's the same in relation to their summer.
So
they
their,
have
their
main
E-season's
season-
during our winter, is that what you're saying?
exactly.
Right, okay.
And what happens as well, which I think is another thing to investigate over time, is why TEP coincidentally happens at the changeover points usually, doesn't it? And are we getting the tail end of a sporadic E-season in one hemisphere interacting with the beginnings in another? So because we think a sporadic TEP is a caudal hop involvement, where exactly is that being involved? Is it at F region, or is there some E stuff in there as well? Don't know, but it's a good question to ask.
Jim, all of that has been amazing and intriguing. All of those words, very interesting. We've had some really interesting talks today, but please give your thanks to Jim.
I only saw 3 closed eyes. If you find the person who's got 3 eyes, you'll know who it is.